So would high-rise buildings really look like this on a globe? Well, the Flat Earth community thinks so. I already made one video on this topic, and that was in regards to a 1,500-foot long warehouse, and the calculations for curvature were well below our tolerances. Now, if you did watch that video, I made a mistake because I said that the roof would be 5/16 of an inch longer than the base on a globe, and it was a pretty stupid mistake. Now, all of my calculations down here are correct, including my conversion from inches to 16ths of an inch, which was 0.48. But for some reason, I wrote it down as 5/16 of an inch, when in reality, it should have been 0.5/16 of an inch or 1/32 of an inch. And that really is no difference at all. Now, I also worked on quite a few high-rise buildings, but of course nothing this tall. This is the 2,037-foot Shanghai Tower in China, which is currently the world's second tallest building. So I went to Google Earth so I could get a measurement of the base down here, and that is 300 feet. And also notice that this tower tapers at the top, which is not uncommon with these very tall buildings. So this will be our hypothetical building. 300 feet at the base, it will be a rectangle so it doesn't taper at the top, and 2,000 feet tall, or 91 meters by 610 meters. So again, on a globe, these would not be perfectly parallel plumb lines. So if the one angle over here is 90 degrees, well, what would this angle over here be? So to calculate this angle down here, I'm going to use the average radius of a globe, 3,959 miles, and the average circumference, 24,875 miles, and 300 feet works out to 0.057 miles. Since the ratio of this angle to 360 degrees is the same as the ratio of 0.057 miles to the circumference of the Earth, I can set up this equation here, and when I do the calculation, it comes up to 0.0008249 degrees. I can also calculate this angle with trigonometry because it's really a long, skinny triangle. And here is the calculation, which gives us the exact same answer. So I'm going to round this off to 0.00082 degrees, which is a really small angle because it's only a little bit bigger than 8/10,000ths of a degree. So the angle on this side would be 89.99918 degrees. So if the base of the building is 300 feet and 2,000 feet tall, then how much longer would the top of the building be than the bottom? So this is another trig calculation because what we have is another long skinny triangle. So I've set it up over here. We're going to use the equation opposite side equals tangent of the angle times the adjacent side. And when I do the calculation, it comes up to 0.0286 feet. Next, I convert feet into inches by multiplying times 12. That gives us 0.3432 inches. And then I'm going to multiply that times 8 to get 2.74. So that works out to be less than 3/8 of an inch. So on a globe, a 2,000-foot tall building with a 300-foot base would have a calculated top that is less than 3/8 of an inch longer. That is less than our tolerances. And these are the calculations in meters for the exact same size building. So the top would be less than a centimeter wider than the bottom. 8.7 millimeters. Now, one method of construction is using structural steel for the framework, and this is where you have columns and beams that are bolted together. But again, we are not building aircraft that require tolerances in the thousandths of an inch. Now, most of my high-rise experience has been on buildings like this that are built entirely out of concrete. Now over here at the top, you can see the formwork for the next deck that is going to be poured. In fact, they are having some type of a concrete pour over here because this white contraption is the boom from a concrete pump truck. Now the pump truck is somewhere down below, and it is attached to a 6-inch slick line that runs up through the center of the building. And that is how we get concrete to the top of the building. Now sometimes we do have smaller pours, and then we'll normally use a bucket that is attached to the crane, and the buckets normally hold 1 yard, which is about 2 tons of concrete. Also notice that they are already installing the exterior curtain on both of these buildings. So I'm just going to give you a very basic idea of how we stay within tolerance for both vertical and horizontal measurements. So let's say these are the columns that are poured on the ground level, and we have our first floor deck forms that are in position. So surveyors are going to come and they're going to transfer benchmarks up to this upper level, and we'll take all of our measurements from those benchmarks. So the first floor has been poured, and the columns above that have also been poured, and now we have the deck forms for the second floor. So again, the surveyors are going to come, they're going to transfer those benchmarks up to the next level so we can take measurements from those benchmarks again. So the reality is that every floor has variations due to construction, and this is why we never take measurements from the existing building. So again, here are the deck forms for the third floor. The surveyors come, give us brand new benchmarks for that level. And every so often we have surveyors from an outside firm come in and check the work of our surveyors to make sure that they are staying within the building tolerances. But again, here is the fourth floor deck, and our surveyors transfer the benchmarks up to that level. And this continues floor after floor after floor until we finally top out the building. So a 2,000-foot tall building would have about 125 floors to it. And as we're working up, that 300-foot length would be measured out on each floor by the carpenters. And if by chance it was 3/8 of an inch bigger on the top, well, that would be within tolerance. And here's a few photographs showing how that exterior curtain is assembled. Now, if you look to the left, you can see they have a whole row of adjustable brackets on the edge of the deck. And if you look down here, you can see that there's a pretty big gap between the edge of the deck and that curtain. Now, what they actually do is they bring in this little miniature crane that they can wheel around on the floor above from where they're attaching these panels. So these panels are assembled on the floor where they'll be used, and you can see here on the left that they have this attached to the crane up above, and they just swing that panel right out through the opening, and then on the right over here they put it into place, and of course they have their own tolerances to work with. So again, flat earthers have it wrong. High-rise buildings would not look like this on a globe. Now here's a photograph of the Seattle skyline. We have the Space Needle over here on the left, and we have the Columbia Center over here on the right, which is the tallest building in Seattle, and the distance between them is 1.4 miles. And here's the calculation showing that the difference between a plumb bob at the Space Needle and one at the Columbia Center is only 0.02 degrees. And since that is only 2/100ths of a degree, of course, you're not going to be able to see this.